thank you so much for having me. And yeah, to everyone, my name is Laurel, and I'm a postdoc, and am really have been thinking for the last year, really, and also some background. I came from the data management community at the University of Washington, so thought a lot about database systems and purely managing data, and then came and did a lot more sort of machine learning, deep learning, and I'm sort of now in this sort of in between worlds right now, and seeing these sort of amazing intersections between the two pipelines, which is pretty exciting to me. And so I kind of want to introduce what I'm thinking of as a new era of feature stores, what I'm calling embedding ecosystems, and some of the sort of exciting challenges that are going to come up with managing these embedding-based pipelines. So there we go. So the outline of my talk, I'm first going to actually go a little bit down memory lane and recall in my mind what is one of the most important sort of and motivating reasons for feature stores, which is the sort of reduction of engineer effort that they allowed in these machine learning pipelines. Now, using that same lens of reducing the engineer effort, I'm going to introduce embedding ecosystems and how really they're just using these self-supervised, which I'll discuss, embedding representations and kind of replacing these manually curated features, and how both systems here are going to speak to the same importance of making it easier for the engineer to build and deploy models. Now, in part 2 of the talk, I'm going to dive more directly into embedding ecosystems and explore some of the upcoming challenges with how do you manage the embeddings and the models at sort of every stage of this pipeline, from the data to the management and then to the downstream models itself. Then at the very end of the talk, I'm going to go into depth into one specific problem, which I've been thinking a lot about recently, which is how do you update these models? But I'll leave with sort of this high-level overview, of all of the sort of different challenges. Okay, so let's dive in. So I'm now going to go through a little bit as what I see as how embedding ecosystems are coming about and how they're kind of the next evolution of feature stores. So this was a phrase taken from a 2015 paper by David Scully called Hidden Technical Debt in Machine Learning Systems, and that was published, I believe, in NeurIPS of that year. And this is, David Scully described the engineer's workflow, and this was before feature stores. So again, the paper was in 2015. And he described, one word that really stuck out to me was this notion of a pipeline jungle, where engineers in their quest to sort of deploy models would have these very customized one-off pipelines, all starting from the data sets, the data sources that they used, the features that they used and defined, what they had to do to get the model into production, and then all the way to the deployed system. And to emphasize the kind of complexity of these pipelines and frankly the headache it caused, this is another well-known figure from that same paper, where they're describing the services, the pieces that need to be in place for a model to put into production. And one of the points here was that little black box, which I've circled in red, was really the only piece that had the core machine learning code, right? The stuff that myself as an academic, I love to write. Like if I could just write that all day, I'd be very happy. But there's all these other systems and components that need to work to get a model deployed. Now, if each of these boxes was a sort of customized pipeline, then it'd be very difficult to maintain these systems in production. And to highlight some of the challenges that this paper introduced, one of them that feature stores are directly addressing is this notion of one-off feature definitions. So for example, if you had separate teams that all needed to have some notion of how popular a product was, each team would have potentially a different definition of it. One team may care about the number of stars, another one may care about the total number of purchases. And so each of those separate definitions are used in a separate downstream model, which can cause some sort of semantic differences in the model performances. Some of the other challenges mentioned in this paper were lack of reproducibility, inconsistent storage, a lack of standard evaluation and testing pipelines. And one of the most important ones is that it's very difficult to detect and recover from errors when you're dealing with these sort of manual one-off pipelines. So in 2018, feature stores were deployed to really help address these issues. And these are systems you all know and love that are really meant to help the engineer build, deploy, and monitor their entire ML pipeline with a specific focus on feature curation and feature management. And one of the most important things here is that it helped make the engineer's life easier. Like it's a hard goal to achieve, but such a simple one at the same time, right? Make their life easier. And that's really, in my mind, what feature stores are allowed to do. Less time had to be spent in each individual team managing these pipelines. But feature stores aren't perfect. And two challenges I want to highlight here, which is going to motivate the embedding ecosystem, is that there still is some handcrafting of features that happens. An engineer still has to go and define at least once, what does it mean to be a popular product? It might be a simple definition, but that still has to happen and be tested and validated. Now, of course, the feature store allows that to be shared across different teams, which is fantastic, but there's still some effort that takes place in that initial feature development process. Now, the other thing is this notion around training data. Many models are what I'd call supervised models, meaning they require labels to be sort of basically handcrafted or generated. And this also takes a lot of engineer effort. You can also get them labeled from a crowd, for example, but that still is going to require effort and cost to go and manually annotate what label you want this example to have. So using these two challenges, I'm now going to describe how self-supervision is really changing the game. So around 2018, 2019 is, in my mind, kind of when self-supervised systems really started to take off. They've been mentioned out for a long time. This is sort of when I saw some of the early work happen here. And self-supervised systems is simply a paradigm where models are going to learn embeddings or vector representations of the underlying data without any manual labels. And so this is going to allow for automatic feature curation without any effort in coming up with labels. So to actually explore what this means, I'm going to walk through a very common example of what a self-supervised system potentially looks like. And so this is one of the most classic textbooks examples of self-supervised training, which is training models and training representations of words. And then these representations can be useful in any task that relates to language. So our goal is to learn some representation that represents a word. Now, a self-supervised task will take a sentence. So for example, the sentence could be the dog enjoys eating bones. Now, this is unlabeled, so I don't have any label in terms of its sentiment or its parse tree or anything. It's just a sentence. So what they do is they actually ask the model to train to basically regurgitate a word after it's been masked out. So what I mean by that is they take a word in the sentence in this style of self-supervised training, and they will mask it. And by mask, it means you basically feed nothing to the model. You null it out, so the model doesn't know what that word is. They then will feed this modified sentence to a standard sort of transformer-based model, for those of you familiar with the architecture, and then ask the model to predict that word. And so what this is doing is it's allowing the model to learn useful signals in terms of word co-occurrence patterns, language structure, in order to predict what that word is. And at the end of the day, the model is going to output representations that encode all of these patterns. And critically, this can be done on any text. You just give me text and I can train a model like this because I don't have to manually label. It's all based on the underlying data itself. And there's a lot of exciting work in other ways that you can learn things without labels, but this is one style based on language. And so here again, the words are going to encode useful information. So how is this used, as I see it, in these embedding ecosystems? Well, you have these models, this like word model that I just presented that will generate embeddings. Now, these are then used into these downstream deployed systems. So going back to that language model example where you have this model that has these word representations, you can then use these representations in some very simple downstream systems that do, sentiment analysis, for example. And then these are the downstream systems that are now deployed. So going back to the standard feature store architecture pipeline that we saw earlier, what embedding ecosystems are doing is really changing these two components here. They're training what is stored and the data that you're using to train these embeddings. And so I'm defining these embedding ecosystems as the self-supervised training data, the embeddings themselves and the embedding models that generate them, and all the systems, the deployed system that use them. This is what I'm defining as this embedding ecosystem that is sort of coming in as sort of a new style of feature store. And the critical things here is that you don't need manual labels to train these representations. It's all without hand engineered effort, which is really, again, reducing that engineering effort. Secondly, you don't have to craft features either. These representations are your features, and they're learned from some model that you don't have to sort of control in the same way. Now, another huge benefit of these things is that when you use these embeddings into downstream systems, you oftentimes see a dramatic improvement in quality, and you oftentimes need less data to train this downstream model. So you will still need some labeled data for that downstream system, but there's a lot of work showing how the style of, another term for it is transfer learning, can help reduce the amount of labeled data that you need. So the overall takeaway is that these embedding ecosystems are in some level doing the same thing that feature stores did. They're helping make the life easier of the engineer in building and deploying models. So this is not a new trend. We're just seeing it come back in a new way. Now, these systems are also far from being perfect, and there's a lot of open challenges in how you can manage the data, the embeddings, and the models. And so in this next part of the talk, I'm going to dive into a little bit as to what I see are some of the most prevalent challenges to maintaining these embedding ecosystems. And I warn you, I have solutions for basically none of them. So they're all very open challenges that I think the community will have to address in the next few years. So we have these three parts of the pipeline. We have the data, this embedding storage and maintenance, and then sort of model deployment. And at a high level, there are challenges with each of those. So in terms of the self-supervised data, you're now dealing with a different style of data. This data is oftentimes much larger, and you have to sort of manage it for these models. And now one very common challenge with this self-supervised data is it's oftentimes is biased. It has different styles of biases in there. And one of the most common ones that I see a lot is popularity bias. And by that, I mean, it doesn't always represent rarer things that can be really important to production pipelines. So I'm going to give an example later about a task that looks at entities, but entities is a common example where there's a lot of very rare things. There are rare songs, rare people that users are still going to ask about, but are not going to be in this sort of these common self-supervised data sets. And so you need to have ways of sort of data engineering to allow models to do better over these rare things and these rare things. So another trend that's coming is because these things are all, in essence, all this data is being trained into one representation space, there's a lot of work in how do you handle multimodal data. You can actually train representations that leverage both text and images, or I mean, videos are sort of more challenging, but you get these multimodal style representations. And so from the data engineering perspective, you're going to have to be able to manage and integrate these different styles of data, from unstructured text to structural relational data, manage them and integrate them to allow these models to be trained over them. And this is something that's very exciting because the structured data can help with other challenges too. Now, the last one is simply the scale, right? These models are oftentimes trained over massive corpora of data, both coming from open source data sets like Wikipedia, as well as company specific data. And so just managing the scale and training efficiently and allowing users to analyze the data and potentially clean it and filter it is also just going to be a challenge in purely managing the size. So now we're moving on to three challenges in how do you manage these embeddings. And here I'm not sort of talking about from exactly what systems to use, but more what are some of the fundamental interactions that some sort of embedded management is going to will have to maintain. So for one, I think search is going to be a really difficult challenge here. Users now will sometimes want to look and see what features they want to use. You're going to have that exact same problem with embeddings. You're going to have a company that will have numerous different pre-trained embeddings, maybe for words, maybe for entities, maybe for images. And an engineer is going to know, what embedding do I use for the system that I'm trying to train? And that gets to be really difficult to search over because you're dealing with these abstract representations, and it's unclear how to even begin understanding what embeddings are going to be good for different downstream tasks. But there has certainly been work showing that different styles of embeddings work better and worse depending on what you want to do with them. So I think simply allowing users to navigate, query over embeddings is going to be an interesting challenge. provenance, I think, is going to be huge. You have to understand how your data impacts representations and what data was used for these representations. And this gets, again, challenging because you don't have a specific definition of what went into the embedding. You were trained over this large data set, and you have to go back and tell me, hey, look, this chunk of data is causing this degradation in performance. That style of provenance is very difficult, but it's going to be very important to be able to maintain high quality representations and make sure that your data is the quality that you want as well. And lastly, a problem that I'm going to come back to later is how do you update these representations? These models, as I said, are trained over very large data sets. And so they take a long time to train, which means you cannot just retrain them every single time some new data comes in. You have to be much smarter about how you update these representations to help hopefully have them be closer to streaming style if you can. Now, lastly, there are some challenges now with how do you deal with the model, or the end model, this sort of downstream deployed model that's using these representations that's being seen by the user. And some of these challenges are not unique to embedding ecosystems, but are, I think, more difficult. So one of them is simply you need to support interfaces for the user to be in the loop with what the model is predicting. You have to have the right style of data structure and data management to allow them to interactively engage with model predictions and potentially the underlying training data that impacted the model, which again, all relates back to handling the scale of the data and being able to understand sort of embedding provenance. So all of these challenges are interrelated. Another increasing challenge is this ability to find slices or subpopulations that are underperforming for the model. Now, again, as I said, this data is oftentimes biased. You don't necessarily have an equal representation of everything. And so it's even more tricky, but important to find rare yet underrepresented subpopulations so an engineer can understand the performance and potentially go and fix it. And the last piece is how do you actually correct these models, right? As you all know, models make mistakes. It's impossible to make a perfect model at the beginning. You have to have the right workflow to support an engineer to engage with these predictions and then fix an error. Now, in these ecosystems, you're dealing with this complex interdependency between the downstream system and the embeddings that the system used. And so you have to be able to understand, if I have an error in the model, where is it coming from? Is it just from my downstream system? Maybe that data is dirty, maybe the model's wrong, or is it coming from the embeddings? Maybe my representations are out of date. Once I figure out the challenge, I have to now be able to fix it. How do I patch an embedding in a way that then means that it's consistently fixed for all downstream systems that use it? How do I even patch a downstream model? So you're dealing with this, again, complex workflow that you have to have the engineers sort of engage with to be able to support these embeddings. Okay, so those are a highlight of, I think, some of the most interesting challenges that are coming up with managing these systems. And now I'm going to deep dive into one specific problem with embeddings and how do you update them. Wait, so okay, so and this is something that I've been spending some time on recently and think a lot about and find it a pretty interesting challenge. Okay, so I'm going to give a grounding use case of this task called named entity disambiguation. And I'm going to use this use case to sort of better motivate this problem later on. So NED, for short, is simply the task of taking some sentence and detecting entities in a knowledge base that participate in that sentence. So if you had a sentence that was, how tall is Lincoln, the NED system would want to extract that Lincoln is an entity. So that's this task. And NED is actually used for both pre-training, and then it can also be helpful in the downstream task itself, but it's a way of learning entity representations. So to show that, again, we have this embedding pipeline here. So entity disambiguation systems are commonly trained, or at least in part trained, on data sets like Wikipedia, right? It's a very large pre-training corpus that has entity annotations for you that you can use. So there might be a sentence about Lincoln in Wikipedia, and you can actually use that to train these models, to pre-train these models to be able to learn representations and predict entities in the task. So you use this large data set, you'll pre-train these entity embeddings, and then these are going to be what's stored in your embedding storage system. So you're going to have representations for Lincoln the president, Lincoln the car, Lincoln the city in Nebraska, Lincoln in Illinois. All the different Lincolns are going to have representations here. Now, how this is used downstream is when you have models that are doing personal assistance, search, QA, information retrieval, it's important to be able to leverage these entity representations in these downstream models. So again, if I had that question, how tall is Lincoln? I need to know what Lincoln I'm referring to in order to be able to answer that question. So some of these models work by first using an NED system to extract that entity, use that representation, that pre-trained representation that's in the embedding store, and then feeding that to some QA model or some knowledge-based query system to actually go and retrieve the answer. So this is the use case I want you to keep in mind when I'm now introducing the challenge of embedding updates. So the fundamental issue is that, especially in terms of entity knowledge is changing all the time. There's about 600 new pages in Wikipedia every day for the last year. And each of these entities in Wikipedia, as I showed earlier, all get entity representations. So you have this rate of change in your knowledge, and you also have entities that are removed, maybe their metadata has changed, and this happens fairly frequently. Also, if you're doing something with recommender pipelines, it's common you can pre-train representations for sellers or consumers or products. And here you're seeing that for at least the Amazon marketplace, you get about 70 new sellers every hour, right? So this is a lot of changes happening every day. Now, the fundamental issue is not so much that the knowledge is changing, but that it's changing at a rate that's oftentimes too fast to keep up with. So these pre-trained models are trained on the order of every week to month, right? These things take a lot of data. They're very expensive to train, and you cannot train them every day. It's just too expensive. So they're trained less frequently. Now, these downstream systems are oftentimes lighter weight. They can be trained on the order of maybe every day or hour. But again, you have this entity knowledge that's updated every day potentially. And so you're at this fundamental frequency mismatch where you cannot retrain these embedding systems at a rate that keeps up with the rate that new knowledge is coming in. And so now you're faced with this issue of how do I update these models more efficiently to avoid this sort of this retraining cost. Now, a natural solution, something that feature stores have done very well, is to treat things streaming. Can I have streaming features? Can I support that type of pipeline? Well, and that's a great question. So let's try and see what happens. So so this is an experiment on, again, this NED task where I treated updated knowledge, new information, basically like a stream of information. I would go and as the data came in, would basically update the model once and to see what happened over the course of some amount of time as you basically streaming update a model. And what you see here is this fundamental challenge with some of these deep learning systems, which in some places the term is called catastrophic forgetting to sound very grandiose about it. But in essence, what's happening here when you're dealing with these entity tasks is you're forgetting old information. And so here you have a plot, which is looking at sort of the time frame that I was doing this streaming update. And you have your model's performance on new entities or new knowledge versus old knowledge. And you see here this fundamental trade-off. It is forgetting old things that it's not seeing in the stream, and it's learning the new things, right? So if your system only cares about very, very recent information, maybe this is okay for you and you can totally streaming update this model. But for some systems like QA, users are going to ask about old entities that aren't updated very frequently. They're still going to ask about how tall Lincoln is. So it's very important that you maintain these models' performance and not forget old information. And so you're at this issue here where you can't really treat these things as streaming anymore. You can't update these models that efficiently. So you need to be a little smarter with how you retrain them. Now, the solution that I'm going to present is very based on the data, right? Is how can I come up with a data set that's smaller so I can train these things more efficiently, more quickly, but without having to pay the cost of iterating over this large corpus? And now there's two things we have to keep in mind here. Performance over popular entities needs to be maintained as well. And in addition, you also have to maintain performance over rare entities. And I hinted at earlier that this notion that structured data can be really useful, that integration challenge that I mentioned earlier. Well, it's known from some prior work that structured knowledge really helps over rare things. And so when you're coming up with how do I select data for a faster update that isn't streaming, the idea is I want to have my new knowledge. I want to have very popular old things that I don't want my model to forget. And I need to make sure to maintain my structured data because that's going to be what's going to allow me to maintain performance over my rare things. So you just have to make sure that you have all the information that you need to make sure the model doesn't forget information. And so some very preliminary sort of proof of concept ideas here, you can show that, the blue models of stuff that starts to forget old knowledge, and you see that on the right-hand side. So a simple random sample over all your data might do well on old stuff, but it's going to forget the new stuff. You really need this sort of balanced sample between structured knowledge, popular information, and new knowledge in order to maintain performance of the model. But you can do this all with a fairly small sample size. So in essence, you're closer to a streaming level performance, but without having to lose information. So I'm going to sort of wrap up here, but a takeaway from this whole update challenge, which is something that I am very excited about, is this high level notion of how do I think about managing and integrating unstructured sources and structured knowledge, right? And feature stores, in my mind, handle structured knowledge very well. That's something that they know how to do. And so there's some interesting challenges and solutions. And how do I think about ways of integrating this knowledge and using it to address some of those challenges I saw earlier, right? Structured data, as I said, can help with some of the popularity biases. It can help with this updatable information. And so there's some really interesting sort of interdependencies and with how do I think about these embedding ecosystems along with some of the well-known sort of structured data challenges from feature stores. So yeah, that is my sort of spiel on embedding ecosystems, and happy to take questions